We use elimination to solve the system of equations. In this case, we have 3 unknowns and 3 equations, and we found a single solution. And then we started talking about matrices and how we create a matrix and what the numbers mean and how the entries are of the numbers are. How do we arrange the numbers associated with the rows, which are the equations, and the columns, which are the variables. And then we included this thing called the augmented matrix, which is just including that additional column of constants. And then we're getting into the nitty gritty of linear algebra, in particular with the matrices that's involved, and that deals with elementary row operations. And we talked about the 3 different kinds of row operations that are legal, that are moves that are applicable to matrices, and how reducing, well, we're going to talk about the word reduce a lot more now. Essentially what we did, and I think we had a whole bunch of other things written down. What we did was we took the matrix and we performed elementary row operations to the matrix in such a way that this matrix that we have, not including the column part of the augmented matrix, but the columns that don't include that augmented part, they have to become a matrix that looks like having a 1 in the diagonals. So in the diagonal entries, they're all 1s and 0s everywhere else. Once we're able to accomplish that, then we're done. And in doing so, what we just accomplished was solving the system of equations for the numerical values for each variable that we have. And I think we also, didn't we? Thought we also did this for 3-dimensional example. Looks like I'm missing it. But didn't we do a 3-dimensional example? Or is that what we didn't do? I think I have something missing here.
We stopped here on the last lesson.
Yeah, this is what we
so
stopped.
we didn't do the 3-dimensional one, right?
No, I don't think so.
Okay, so I think that's what I wanted to do now. So let me, I thought we had, okay. So just to get our feet wet again, we have this system, right? And we already know the solution to this. We already have finished it. And the solution was what? Was it 1, 2, 3? Wow, very nice. So the solution to the system, we already know what it is. It's 1, 2, 3, right? We already know this. Okay, so now let's apply what we've learned with elementary row operations to this system. So the first thing is I want to create a matrix, right? And the matrix is going to be a matrix that has 3 rows because I have 3 equations, and I'm going to have 4 columns because I have 3 variables plus that column of constants. So I'm going to have something like this, right? 1, 2, 1, 1, 2, 2, 4, -3, 3, 6, -5. And then I'm gonna have this dotted line here, and I'm gonna have this 1, 9, 1, 0. So this is my matrix, right? So I created my matrix from the system. Okay, now I already know though, right? I already know that this will be the column for the x variables, the y and the z. And this is gonna be equation 1, equation 2, equation 3. But now we're going to be considering this as a row. So these are my rows. And then I have my columns. Rows and columns. That's basically what matrices are. And now we know how to arrange it. Okay. Now, what's the goal? What's my goal here? My goal is to solve the system, of course. But in terms of the matrices, what I want is 1, 0, 0 for the first column. I want the second column to look like 0, 1, 0. And for the third column to look like 0, 0, 1. That's my goal. Now, whatever happens here happens. And we already know what's going to look like. It's going to look like 1, 2, 3. But my goal is to make this coefficient matrix make this all ones on the diagonal and zeros everywhere else. So does anybody know what the first step should be? What's my first operation that I should do or I could do to get this process going? Anybody? So I have this 1 here. I want to get rid of this 2 underneath it. I want to make this a 0. So what am I supposed to do to that first row so that I apply it to the second row and I get rid of that 2?
Do you multiply by 2?
I multiply what by 2?
By the first row.
The first row. That's right. So I say what? What do I say? I say -2, right? I multiply not by 2, but by -2.
Yes.
So that when I multiply -2 by 1, right? This becomes -2. When I add to +2, I get 0. So I multiply our row 1 by -2. I add it to the second row and I make that the second row. Correct? So then the first row is left untouched. That's the same. And then what do I do after that? I add the multiple of the first row, which is multiplied by -2, and I add it to the second row and I make that the new row. So 1 times -2 is -2 plus 2. This becomes 0. So I'm gonna do some of this in my head. I'm not gonna write out every computation. -2 plus 4 is +2. -2 times 2 is -4 minus 3 is -7, and then 9 times -2 is -18 plus 1 is -17, right? Does everybody see that? Okay, guys, you have to mute yourselves because I can hear some music in the background. Somebody's playing some good tunes out
Mexicans
there.
1 second after a baby is born.
So I don't know who that is, but please mute yourselves, please. Thank you. TikTok, is that what it is?
Yeah.
I don't know about that stuff, man. Okay, so what's the next row? I mean, what's the next step?
Is to try to get 1 in the second column.
1 in the second column. Yeah, but I want to get rid of the 3 first. I want to get rid of the first column, get all the zeros underneath 1. So let me just do that in one step, right? So then there we go, Mir. So we say -3 R1, we add it to R3 and make that my new row. So what I just did in this first little step here is I got rid of the 0 underneath the 1, the first one, and the 0 underneath I'm basically clearing out all the numbers underneath this 1. So this is 1. I want to make all these underneath zeros. And so when I multiply 1 by -3, I add it to 3, I get 0. Let me change that 0. And then 1 times -3, I add it to 6, I get 3. 2 times -3 is -6, plus -5 is -11. And then 9 times -3 is -27, plus 0 is -27. Everyone okay with this?
Yep.
So far, everything's okay. Okay, so now we've accomplished that first column, 1 0 0. Now I want to do the same thing now for the second column, but the second column, I want that middle entry, right? I want 2, this number here, I want this to become a 1. So what's the first thing I have to do? Well, do you do the first column, then second, then third? Yes, Leonardo. So the idea is that we're gonna slowly, step by step, take care of each column. So the first column we took care of. It's a 1 0 0. Great, check. Now next column is 1 2 3. So the first thing is I want to get rid of, I want to rewrite this 2 somehow. And so ZU says, take half. So for this step here, take half of R2 and make that R2. So remember, these are steps that I can do, right? From the previous lecture. We discussed the different elementary row operations that are possible. I can apply these row operations. I can multiply a row by a non-zero constant. So I just did that. I multiplied row 2 by a non-zero constant, which is a half. In doing so, now I'm going to be dealing with fractions. It's not going to be that pretty, but again, we already know how this story ends. We already know. So if we do every step correct, it should work out. So now this 2 becomes a 1. This -7 halves, -7 becomes -7 halves. And this -17 becomes -17/2. And I get 0, 3, -11, -27. Okay, now I have this 1 here, second column. Now what do I need to do? I need to get rid of this 3. How come row 1 is allowed to stay the same? Well, if you notice, Tosif, I'm applying, so these 2 steps that I've done so far, I'm applying it to a different row. I haven't applied I haven't applied it to row 1. I've used the row 1 to apply it to row 2 and to apply it to row 3. And what happens is that first row tends to be untouched until the end. At the end, you start seeing that so in a way, what we're doing, okay, what we're doing is we're getting rid of the diagonal entries. So these entries should be 1s, right? We're getting rid of this, making this a 0, making this a 0, making this a 0. And then we want to make these entries above the diagonal to be 0 as well. So when we go backwards, that's when these things here clear up. So in a way, we're dealing with this second like lower triangular area region of the matrix. We're making that 0 first. And then we're working our way back to making this upper triangular region of the matrix 0s. So that's the way it goes. If that's the way we're going to be flowing. Yeah, I know at first it's a little weird, but eventually that's the way it is. So I'm going to talk about this and we'll get there. When you make the entries all 1s and everything below that diagonal entries, everything below it, when you make that a 0 and you don't do anything else, so all of these here are also going to be numbers. When you write it in that form, it's called reduced echelon, row echelon form. We're talking about that. And then when you make all of the upper entries 0s as well, it's called reduced row echelon form. So one is called REF, the other one is RREF. And they're there because of different reasons. But our goal is to always put it in row reduced echelon form. And that's just vocabulary that we're going to get accustomed to. But first, I just want to get you guys used to the elementary row operations. So once you have that down pat, then all these terms and different things will make more sense. We use this equation, so can we use it again as if we don't want any fractions? Well, the thing is, it's not that we don't want any fractions. Sometimes we can't help it. It's not that whether we want it or not. It's gonna occur whether or not we want it, right? Like the fractions will appear. Your solutions may be fractions. How can you stop it from being fractions if that's the solution? But so the thing is, we can't apply what you said interpret because we're not multiplying negative. If you're starting from here, we're not multiplying the first row by -3 and then adding it to row 3. Because if we do that, then what's going to happen? This will be negative. This will become that 1 will become -3, and you're adding it to this. It becomes -3. So you're just undoing what you don't want it to be done. Like you're undoing, you want this to be a 0, so you maintain this as 0. So you don't need to use this first row and apply it to row 3 anymore. You're gonna be doing the opposite. You're gonna be using row 3 eventually to apply it to row 1. So for now, all I've done so far is the first column. I've kept this a 1, the first entry, right? And then everything else here are zeros. Second column, the middle entry has to become a 1. I made it a 1. And now I want to get rid of this 3 on the bottom. I want to get rid of this 3. So that, remember, that's how we're doing. We're first making the entries here all 1s. We're making them 1s. And we are making all of these underneath that diagonal entries. We're trying to make all of those entries 0. So far we have 0, 0, and this 3 here, I want to get rid of this 3. So what do I have to do to get rid of that 3? I need to apply elementary row operation. Is this Gaussian elimination? Yes. Yes. So the process that we're doing, guys, is called Jordan-Gauss or Gauss-Jordan elimination. So this whole process, the process of applying a matrix, the row operations, so that we have this kind of thing at the end, that whole process is called, so this process here is called Gauss-Jordan elimination. So the process to go from here to this, that's called the Gauss-Jordan elimination. Again, these are just big words. It's fancy, it sounds fancy. Gauss-Jordan, these are 2 names, very important names, particularly Gauss. Gauss is considered one of the greatest mathematicians, if not the greatest, if not one of the greatest mathematicians ever. Carl Friedrich Gauss, he's German. Okay, so what do I have to apply to the second row to get rid of that 3 in the third row? Anybody?
That would, could we multiply row 2 and then add it to row 3
Right. So what are we going to multiply? We're going to multiply.
by 2?
Well, not by 2. I want to get rid of the 3.
Negative
So,
3.
Oh,
right,
yeah.
right. Negative 3 R2, right? I'm going to add it to row 3, and I'm going to make that my new row for
Yeah.
row 3, right? So now it's going to be 1, 0, 0, 1, 1, 0. So all of that is going to be, right, exactly what we expect. This will be the same. This will be the same. And so now we're going to be dealing with fractions. When we multiply negative 3, I get what? I get negative 21 over 2. When I multiply negative 17 by, sorry, this is negative, right? Sorry about that. Hold on. This is negative 7 halves. And this is going to be negative 17 over 2. And what's going to change is the number underneath. So this will be, so I'm going to break this down a bit. So when I multiply the second row, when I multiply these entries here by negative 3, what do I get? I get negative 21 over 2. And then, so this is negative 3R2, right? Just to break this down, this becomes 0, this becomes negative 3, and this becomes negative 21 over 2, and this becomes negative, huh? 3, right?
Negative
You multiply,
51 over 2.
say it again.
Negative 51 over 2.
Negative 51, right? Negative 51 over 2, and this should be positive because we're multiplying by a negative number. And then the third row is what? The third row is 0, 3, right? R3, 0, 3, negative 11, negative 27. And so when we add these together, we get our new numbers for row 3. We get 0 as expected, right? We got 0, 0. And then we get 21 over 2 minus 11, which is the same thing as saying 22 over 2, right? And then we subtract, you get negative 1/2. So this is the number, negative 1/2. That's my new number in the bottom entry here. And then we do 51 over 2 when you subtract those, right? 51 over 2, this becomes what? Negative 54 over 2. So when you subtract that, what do you get? You get negative 3/2. So that's going to be my last entry here, negative 3/2. So the annoying thing is that we have these fractions to take care of, but it is what it is. That's what we have. So what have we accomplished? What have we accomplished? We've accomplished making all these entries in the lower triangular part of the matrix of this coefficient matrix. We made them equal 0. So that's a heck of a feat so far. Now I want to make this a 1, right? So then what do I have to apply to this last row here to make this entry equal a 1? What do I do? Multiply by, not by 2, but by
Negative.
Positive half.
negative 2. Multiply by negative 2. So we multiply row 3 by negative 2 and make that our new row. So all these entries in the beginning, the first 2 rows are the same. So it's 1, 0, 1, 1, 2, negative 7 over 2, 9, negative 17, 2, right? And now this becomes 0, 0, 1 because negative 1/2 times negative 2 is 1. And negative 3/2 times negative 2 is 3. Isn't this exactly what we expected though? If we stop right here, do you see that these entries, columns here, X, Y, Z? If you interpret this row, how do we interpret this? This is saying Z is equal to 3, right? Because this 1 is associated with the variable Z, and there's nothing else here in this row. So all I did was I basically found that Z is 3, which is exactly what I had known anyways. So let me just say something about this matrix right now. This is what's called, this is a matrix in what's called row echelon form. Okay. Let's see. So we have row echelon form. Now, what is row echelon form? Row echelon form is when you have a matrix and you have a 1 in the diagonals. So I'm going to give you a few more terminology that you need to know. These ones here are called pivots. These are called pivots. Each one of these are called pivots. Let me just extend this. They're called pivots of a column. So that first column here has a pivot, and this pivot is the 1 in this first entry here. This second column here has a 1 in the second entry. That's a pivot. And this is also going to be a pivot. So row reduced echelon form have 1s in their pivots or pivot variables. So why do we care about this? Is that there are going to be instances where we apply this process called the Gauss-Jordan elimination process. When we apply this process, and we're not going to get 1s for every single diagonal, meaning that not every variable will have a pivot variable. Not every variable will have a pivot. And when we have those situations, that's when we have either no solution or infinitely many solutions, right? So these examples are very nice examples because the pivots appear in every column, meaning that the 1s appear in every column. But that doesn't always happen. And so we'll see those examples in a short while. So the row reduced echelon form has the form that we discussed. So it's only considered pivot if the value is 1. Yes. If it's considered a pivot if when you apply the row reduced, like when you apply these elementary row operations, when you apply them, so that you can get this, right? This form, we want to get this as our final form, but that doesn't always happen. but that's our pursuit. That's why we're applying these these elementary row operations. We're trying to make it that first matrix, that little square matrix. We're trying to make that into ones along the diagonal and zeros everywhere else. In our attempt to do so, there might be situations where we don't get a 1 in one of the columns for some reason. The computation just makes it either 0, makes it another number that we can't get rid of. If that happens, then there is no pivot. If it's not possible, and we'll see that. So right now you see all ones, so you think, oh, all of them are going to be ones, and who cares about this because it's always going to be ones, but it's not. And it becomes more interesting when it doesn't happen. So for now, these are the pivots, and the row reduced echelon form is when you have a situation where the ones are on the diagonal, right? The zeros here, and everywhere else though, they still have numbers. You still have numbers. The order matters for the goal. What do you mean by that, James? What order? I'm not too sure about what you mean by the order matters. Okay, so these are the pivots. Now, right now it's in it's in row echelon form. And what we want to do is write it into row reduced or reduced row echelon form. Reduced row echelon form is when you have zeros everywhere, above the ones and below the ones. So right now we only have ones below, zeros below the ones. So when we have zeros below the ones, zeros are below the ones. They're also called leading ones, the leading ones. So these are also called leading ones, aka leading ones. So some of the terminology is a bit clunky. It's not so clear. It's not so clean, you know, but they're called leading ones because for each row, right? They're like the first number. So the first row, the first number here is a 1. In the second row, in the second column, it's a 1. The third row, in the third column, it's a 1. So they're leading ones. So when you have zeros below the leading ones, you have what's called row echelon form. If you have zeros above and below the leading ones, it's called reduced row echelon form. So do you see this? This is what's our goal, reduced row echelon form. In essence, you have completed the task of solving it by just leaving it in row echelon form. We basically solved it at this point. But what we have to do here, if we want to just stop here, we have to do what's called back substitution. So the moment we know this here, we're done with the process, right? Z equals 3, we know that. Now we go back to the previous equation. And the previous equation, what does the previous equation say? It says that, for example, in this equation here, what does it say? It says y plus, or I should say, minus 7/2 z equals negative 17 over 2. I already know what z is. Z is what? From this equation here, z is 3. So y minus 7/2 times 3 equals negative 17 over 2. And then y minus 21 over 2 equals negative 17 over 2. You add negative 20, you add 21 over 2 on both sides. And what do you get? You get y equals 4 over 2, which equals y equals 2, which is what we expect. Now you know what y is, you know what z is, go back to the first equation, and then you plug in those values into that equation, you get what x is. So in essence, and this is what actually, when you make like different programs like Mathematica, when you have different algorithms that solve systems of equations, they don't actually solve everything the way we're going to be doing with reduced row echelon form. Normally what they do is to reduce the computation time is they make it into row echelon form, and then they do back substitution, which is what we're doing here. So this is like what's called back substitution. So back substitution is only applied when elimination stops at row echelon form, which is REF for short. So you can do it that way, or we can go all the way down to row reduced echelon form. So let's just complete our task into row reduced echelon form. So we have this matrix 1, 1, 2, 9. Then you have 0, 1, -7 halves. We all get, okay, hold on. And that's Gaussian elimination as opposed to Gauss-Jordan elimination. Not necessarily. It's just a portion of the Gauss-Jordan elimination. When we get to row echelon form, we just like stop at a particular point, but then we have to apply a different process. We have to apply back substitution. So this is like half, like a portion of the elimination process. We get all 0 except diagonals. Yes, Chaitanya, that's right. In row reduced echelon form, everything are zeros above the ones and below the leading ones. In REF, the zeros are only below. In RREF, I guess let's just say it that way, because usually they like saying row reduced echelon form. But in RREF, the zeros are below and above the leading ones, or where the pivots are. You play it by ear. Well, it depends. It depends upon, first of all, if what the question is asking, if it's a very specific, use row reduced echelon form, use echelon, use RREF or use REF. It depends on the question, and it also depends on if you're comfortable with fractions in this case. Like, are you comfortable with it? And all I'm trying to show you guys is there's more than one way. Because if I just show you one way and I just go move on, you think that's the only way. That's not the only way. So some people solve system of equations by applying Gauss-Jordan elimination, but they only put it in row echelon form. When you do that, you have to apply back substitution to get all the variables. Let's say you don't want to do the back substitution method, then just make that matrix, that whole matrix, and put it in reduced row echelon form, which is basically just applying the same thing backwards, the elimination process just backwards, and then you get the numbers cleanly at the end. Okay, so I just showed you we could stop the elimination process right here and just finish solving the system by applying back substitution. So you use what you got in the last row, and then you apply it to the second row, make that an equation and solve for y. And then once you get y and you got z, apply it to the, I'm not going to do it here, but apply it to the first row, which represents that first equation. You know what y is, you know what z is, then you can solve for x. Or you can just go all the way through this whole process and get the row reduced echelon form. So it's just good to know both ways, basically at this point. And then you can decide which one would suit you better in the example that you're given. So in this case, right, I'm just rewriting this. This is negative 17/2. So this is if I continue. I'm going to continue elimination to get row reduced echelon form. Okay. Why would we need RREF over REF? Because that's a great question, Chaitanya. I guess because we've only dealt with so limited number of examples, which this is the second example that we're applying this method on, and both of these systems that we're dealing with have one solution, it seems as though it's almost like irrelevant, right? Like why do we need this? over the other form if it's good enough. REF is good enough because all we have to do is back substitution and everything works out. The problem with that is, how do you know that the system has one solution? When it has more than one solution or it has no solution, you're not going to get ones on all the diagonals. You're not going to get this clean, beautiful matrix. You're not. You get something different. And then if you want to understand you're gonna see the dependencies between the variables to understand it better, REF is not enough. You need to know RREF. So when you break down RREF, you basically break down the matrix into its most when you do RREF, you take away all the things that you don't need about the matrix, and you understand like the genetic code without being too crazy about it. But you really understand okay, one thing about RREF is that every matrix, I don't care what it is, can always be written as a unique version of, there's one unique version of RREF for each matrix. There's not necessarily a unique version of REF for each matrix. So if you get a matrix and you put in REF, there could be different versions of REF. There could be. But when you put a matrix into RREF form, there's only one of those versions. So it's like understanding the genetic code of a human being. To put a matrix into RREF, you understand the genetic code of that matrix. You understand everything about that matrix. And you'll see why shortly or throughout the lectures as to why RREF is important. In this scenario, when you have one solution, when it works, when things work out really nicely, it doesn't really make a difference. When things don't work nicely, RREF, you'll see the difference, the distinction between these two forms. So if we get REF and get 0 in a row in every position, so in order to understand this, yeah, so we'll first finish this. Let's finish this. Let's see what it looks like, right? We already know what it looks like, and then we'll deal with things that don't work out, and then you'll see why we care about RREF a bit more. Okay. So let's finish this. So we got ones here, right? And so we got 1, 3. Okay. So again, in this position, in this scenario right now, my matrix is in RREF form, right? Or REF, sorry. REF form. Why is it in REF form? Well, it has ones in the diagonal. It has zeros below it. And that's what the REF form is. Now I want to clear the zeros, the entries above the ones. I want to clear that, it's making them zeros. So then once I accomplish that, then this matrix is no longer in REF form, it's in RREF form. So I have to do a few more things. First of all, I have to get rid of, what I have to get rid of? I got to get rid of this entry above this one, because I want to get all the zeros above this one, the zeros above this one, right? And I don't have to worry about this. But just the entries above this one and the entries above this one, I have to make them zeros. So now I go backwards, which is kind of the process of what we did here with back substitution. But in back substitution, we're just plugging in numbers and solving for y. In this case, we're just making these zeros. So what do I have to do to get this become a 0?
You can multiply the last row by 7.5 and add it to the second row.
Right. I do 7/2 R3 added to R2, which makes this our new row. So when I do that, I get 1, 0, 0, 0, 1, 3. This will be the same. This will be 1. This will be 0 because that's exactly what I just did. I'm eliminating that 7/2. Now, what is this number here going to be? This number right here. Well, if I multiply this by what? 7/2, what do I get? I get 21/2. And I'm adding this to what? What is this? This is -17/2, right? What is this? Isn't this 4/2? Isn't this 2? Isn't this exactly what's supposed to be? 2? Do you guys see that? Didn't we apply, didn't we look at this computation? Didn't we do this computation somewhere? It's right here. The computation of back substitution is also performed in this process of going from REF to RREF. It's embedded in it. It's just that one way is doing it as if we forget about the elimination process and we just go as if we have equations and we're plugging in numbers. In this process, we forget about the equations and we're just dealing with the numbers. Do you see that? Do you see the difference? The difference, yet we're doing the same thing. We're doing the same exact thing. Okay, so that's this entry. And what did I just do? What did I just accomplish? Z equals 3, y equals 2. I already know this, right? And then negative, what is -5? What do you mean by -5, Mir? I'm not following that. So far I've solved for y and for z and making it into RREF, but I still haven't. Okay, no problem. I still haven't made this into RREF form yet. So I still have these ones here, right? I still have 1, 2, and 9. So I want to get rid of this guy. I want to get rid of this guy. So how do I get rid of this 2? Shouldn't be that hard anymore, right? Because it's just a 2. So I want to get rid of this 2. I use this 1, multiply it by negative, and then just add it. Do you see that? So then let's do that. So I'm going to do -2 R3, add it to R1, make that R1. And so when I do that, I get 1, 0, 0, 1, 1, 0, 1, 0, 0. It has to be 0 because when I multiply 1 by -2 and add it to 2, I get 0. When I multiply 3 by -2, I get -6. When I add it to 9, I get what? 3. So in a way, we can just stop here as well, right? We can stop here because I know what this is. I know what this means. This means y equals 2. I know what this means. This row here means z equals 3. And then what does this mean? This means that x plus y equals 3. Well, if I know what y is, this is 2. X plus 2 is 3, so x is 1. Do you guys see that? I can stop here technically. But it's not in row reduced echelon form because this 1 here is still not a 0. So one more step and we're done. One more step. The last step is -1 or negative R2 plus R1. You go into R1. And when you do that, what happens? I get 1, 0, 0, 1, 0, 1, 0, 2, 0, 0, 1, 3. And this is in what form? This is in RREF form. What information do I get from this? I get the solution. X equals 1, y equals 2, and z equals 3. Okay, so the purpose of these examples is to get used to elementary row operations. And then once we get used to the elementary row operations, then we start seeing that there are different kinds of forms of matrices that we get to. One being row echelon form, the other one being reduced row echelon form. Of course, these examples that we've done, they have one solution, so it doesn't make much of a difference. But when we have problems where it's not going to be this clean, this nice every time, we'll see why row reduced echelon form is actually important. Can you scroll up a bit? Yes, I can try to do that. Let me just see what people have said. Is there any benefit to getting all the way into row reduced echelon form if you can calculate the solution at an earlier point? Yeah, that's what I was saying, Sam. Okay, so first of all, we're dealing with 3x3 systems. It's not that much more than a 2x2 system, even though just going to that from second two-dimensional space to three-dimensional space, there's already a big switch with the geometry of things, right? And that additional column and additional row creates more computation that's required. So at this point, it may not seem like a big deal doing row reduced echelon form, row echelon form doesn't make much of a difference. You can stop at like after you reach row echelon form, you can stop there. You can stop and then solve the system. That's okay. Because this system is solvable. What if you have systems that are not solvable? Right? The different forms will differentiate, the distinction of it will be differentiated when you see these situations arise. And I would say in row reduced echelon form, it becomes much more important when you have problems where you have infinitely many solutions. Because you'll be able to see the dependencies of the variables. When you have something that's independent, when you have something that the system, there's more than one solution, you have to see how the variables depend upon the other variable, and you'll see that not in this example. How would you personally test given? How would you personally test given equations for solutions? Okay, so see, Ken, again, this is a 3x3 system. The problem becomes when the system gets bigger, 4x4, 5x5, 10x10, so on and so forth, right? How can I explain this? So for those of you who've taken calculus, right? When you learn calculus, you learn about derivatives. What's the first thing you learn about derivatives? You learn about the difference quotient, you apply the limit, and then you do like, you do the f of x plus h minus f of x over h, and then they give you functions and they say, oh, find the derivative using this definition, and you're doing all this work algebraically, and you get this final answer at the end, right? So you do all this, like for example, find a derivative of x squared. We know it's 2x, but then the way they teach you is they first teach you to write this limit, and then you do all this computation, things cancel out, the h's cancel out, you take the limit, h goes to 0, and you get 2x at the end. I'm using that analogy for this. We're doing all this work with computations, this, that, and third to find solutions, right? Eventually, we're not going to be doing this throughout the whole semester. We're not, because this is going to get crazy, right? Doing this, imagine a 10x10 system. We're not going to be doing this. We're not. We may have calculators that do this for us. As we start getting more advanced with the matrix, the theory behind the matrix, because there's a lot of theory. It's not computation when we get to that point. There's a lot of theory behind it. You can figure out whether something has infinitely many solutions, no solutions, or one solution by different factors. We're not there yet. We're definitely not there yet. We're just getting our feet underneath us. There's something that's called determinants. I've probably heard of it, determinants, before, but the determinant of a matrix is an indicator of whether or not you have one solution or not. Okay, so there will be ways to test whether a system has infinitely many solutions, no solutions, in a much rapid way, rather than having to write it all the way down to row reduced echelon form, which is not feasible, and nor is it recommended for every system. But this is just like the building blocks that we're going through. Okay. Okay, yeah, this is just the beginning. Okay, so that's row reduced echelon form, row echelon form. Okay. So in this particular example, we have one solution. We're not always going to be saying one solution. We're going to be using a more precise way of saying one solution. We're going to be saying there's a unique solution. So AKA one, right? Because unique means there's only one. So this word unique will be used a lot more in this class. We're not going to be saying one solution anymore. We're going to be saying a unique solution. So this system has a unique solution. There may be systems that don't have unique solutions. They have infinitely many solutions. Okay. Okay, so let's look at different examples here. So I'm gonna give you examples of matrices in RREF. So the first example here is a matrix 1, 0, 0, 0, 1, 0, 0, 2, 0, 0, 0, 1. So we're gonna make believe that this is the augmented matrix, and we wrote it in row reduced echelon form. Now, do you see what kind of system this is just by looking at this? The pivots, what are the pivots? The pivots are in the diagonals, right? I got a 1 here, I got a 1 here, but there is no pivot here because this is a 0, it's not a 1. So in the process of trying to get it into row reduced echelon form and trying to get this to be a 1, in our pursuit, somewhere down the line, this became a 0. Now, how do you, either no solutions or infinitely many, but how do you determine which one is correct? Well, we can just interpret this. How do we interpret the first row? I mean, the first, second, and third row. How do we interpret it? The first row, what does it mean?
It means x equals 1. The second one, like y equals
first
1.
row, x equals 0.
Oh.
X equals 0. The second row is what? X plus 2y
equals 0.
Equals 0.
Mhm.
And then the third row is what?
X plus y plus z equals 0.
No. I
No,
got
the
zeros
second-
for
the
X, I
second
got
row.
0 for Y, and I got 0 for Z. What, someone's gonna say something?
The second row means y plus 2z equals
Oh,
0.
yes, you're right. Not X, sorry, pardon me for that. You're right, this is Y, this is Z, right? Because the first column is what, X, the second column is what, Y, and the third column here is Z. That's right. So it's Y plus 2Z is 0. And then the last row is what? 0x plus 0y plus 0z is 1. In other words, 0 equals 1. Is that true? Obviously not, right? 0 doesn't equal 1. So when we have a system that looks like this, then what do we say? Is there infinitely many or no solution?
No solution.
There's
No solution. Yeah.
That's right. So this is an example. This is an example of a matrix in row reduced echelon form that indicates that there is no solution. Why is there no solution? Because that bottom row, we have zeros all across, except for that last number. And if we were to interpret that row as an equation, we get something that's erroneous. It doesn't make sense. So this is an example of a row reduced echelon form with no solution. The thing is, in row echelon form, we may not necessarily get that information. So that's why we get that, we write into row reduced echelon form. Let's look at another example.
Professor?
Yes.
Yeah, I have a question. So for the
Sure.
example, so is it a RREF or it's not?
It is RREF. Now,
But
why is it RREF?
Yeah, I'm confused.
Yeah, it's RREF because how do you get a matrix in RREF form? You try to get the ones, right? The ones in the diagonal. So we have a 1 here in the diagonal, we have a 1 here in the diagonal, right? But the next diagonal, we don't have a 1. But that happens sometimes. So what we have here, we have 2 pivots, not 3. The previous example that we were dealing with had 3 pivots because everything worked out very nicely. And this example, this is just an example, right? We haven't even done all the elimination process, but we're making believe that we've done the elimination process and we get this matrix. We have 1s in the diagonal, which is part of the row reduced echelon form, right? But
Yeah.
what makes this RREF is that all the zeros below the 1 and above the 1, there's zeros below and above the leading ones, or where the pivots are, there's zeros below and above it. That's why it's RREF.
Oh, okay, I got
So
it.
like the
because-
moment this has like
Uh,
a 3 or something, it's not RREF.
Okay,
This could be a 3,
it's by the
this
last
could be a
row,
5.
so-
Right?
Yeah.
But the moment you have zeros above and below every leading one, then it's row reduced echelon form.
Okay, I got it. Thank
Okay,
you.
yeah. So this is all about getting more experience, more exposure to this. Again, we're just starting little by little. So I'll give you another one. I'll give you one that is like this: 1, 0, 0, 0, 1, 0, 3, -4, 0, -1, 2, 0. So this is another example of row reduced echelon form. Why? Because in this example, we have ones in the diagonal, there's zeros below it, there's zeros above it, and this one here is also a 0. It's a 0, it's not a 1. So this is row reduced echelon form because all the leading ones. Why doesn't the last one have to have a 1 to be considered RREF? Because there are situations where the leading one, that this one here doesn't appear in every entry in the diagonal of the coefficient matrix. Like sometimes when you apply the elementary row operations, things cancel out where that last row, it just becomes all zeros. It just happens to be that. And so then when that happens, the only places that are where the ones appear, we call those the pivots. And so when that happens, these are the only ones that we care about in a way. So you don't need this last one to be a 1 to be considered row reduced echelon form. It's just that we start out with an example where everything works out. So row reduced echelon form, when things work out with one unique solution, it's almost in a way we say it's kind of boring. Why is it boring? So when a system has a unique solution, the row reduced echelon form will always be 1, 1, 1, 1, 1. For example, in a 3 by 3 matrix, right? And you have numbers here. Every 3 by 3 matrix, every 3 by 3 system, and we include this augmented matrix, right? When you take a 3 by 3 3 by 3 system that has one solution and you perform elementary row operations, when you perform Gauss-Jordan elimination to it, to a point to get it in row reduced echelon form, this part of the matrix will always be ones in the diagonal, zeros everywhere else. And then this augmented matrix will be whatever the numbers are. So that's expected. The problem is when you have a system that does not have one solution, a unique solution, or it's a system that has infinitely many solutions or no solution. When we apply this elimination process and we try to get it with having ones in the diagonal all the way across and zeros everywhere else, something breaks down. And when it breaks down, it breaks down. There's nothing we can do about it. This 0 appears because it became a 0 in trying to make it a 1 in a way. You understand? Like in our pursuit, in trying to make all these ones, it becomes a 0 somehow through the computation. It just goes away. Same thing when you solve a system without this elimination method. When you solve a system normally, right? When you use substitution method or elimination method in the 2 by 2 case, situations arise where all the variables disappear, right? Remember that? Well, all the variables disappear when you get a 3 = 3 at the end or something like that. What do you say? Infinitely many solutions. Or when you try to do elimination process and you get like at the end you get like 3 = 1, for example. What do you say? No solution. So things break down. So you don't always get what you think you're gonna get. So when that happens, we just accept it. We just say, oh, we only see ones here, so that's it. So because we only see ones here, this is an X, this is a Y, this is a Z. How do we interpret the rows? What does the first row say? It says X plus 3Z equals -1. And then we get the second row is what? Y minus 4z equals 2. And what does the third row say? 0 equals 0. Is there a situation where 1 doesn't end up in none of the rows? if you apply Gauss-Jordan elimination to a matrix and you don't get a leading 1, the only way that's possible is if you have a matrix that are all zeros. Okay, Xavier, it's good questions. Great questions, by the way. I love this. And Mir, yes, in this situation, there's infinitely many. And then how do you know that? Well, let's see what happens, right? If we look at the equations, x plus 3z minus 1, and we get y minus 4z equals to 2. So in our pursuit of writing this matrix in row reduced echelon form, we notice that not every column XYZ has a 1 in it. So the columns that have a 1 in it indicate that those variables are called pivot variables. That's one example here. So let me just move this a little bit. So what are the pivot variables in this example? So pivot variables are the variables that have a leading 1 in its respective column. Respective column. In row reduced echelon form. So in this example, what are the pivot variables? X and Y. Why is that? Because when you put it in row reduced echelon form, the 1 in the first row indicates that X is a pivot, and so is Y. So those are called the pivot variables. And then what do you call the variables that don't have a 1 in it? For example, Z, right? Z doesn't have a leading 1. The leading 1 should be here, but it's not there. It's 0. So what are those called? They're called free variables. They're free. So they're the variables that do not have a leading 1 in its respective column in row reduced echelon form. So what's the free variable? Z. So I'm just gonna write this as an example here. This is the X and Y variable. And then what about this one here? It's Z. And then you may say, but what does that mean? Free and pivot. What does that mean? In a way, think of pivot. I don't know why I use the word pivot. Maybe think of it as something fixed. X and Y are in a way fixed whenever Z is chosen. What do I mean by that? If you look at the first equation that we get here and the second equation here, why don't you solve for X in the first equation? So in the first equation, what is X going to equal? X equals -1 minus 3Z. And in the second equation, what does Y equal? Y equals 2 plus 4Z. Do you see how X and Y are both dependent upon Z? Z could be anything. Choose anything for Z, hence the name free. It's free. You can choose Z to be anything. The moment you choose Z, X and Y are fixed. They're immediately determined what they are. And that's why there's infinitely many solutions. It's because there's one free variable. It's because that variable doesn't have a leading one in its row reduced echelon form. And do you see now why maybe, hopefully, row reduced echelon form gives you a bit more information than the row echelon form with systems that don't have just a unique solution, when they have infinitely many more, or if they have no solution. So this has infinitely many solutions. And with the row reduced echelon form, I know exactly what the relationship is with x and z, y and z. I know exactly what it is. And then how would I write the infinitely many solutions? How would I write that? Well, I would write that exactly the way it's written down. X is what? -1 minus 3z, comma. This is what? 2 plus 4z, comma, z. Do you guys follow? Does everybody follow this? In this system, infinitely many solutions is written in this way. And it's dependent upon what z is. X is dependent upon z, y is dependent upon z. How is it dependent? Well, when we put z, x is -1 minus 3z, y is 2 plus 4z. And I was able to recognize this because it's in row reduced echelon form. Okay, so it actually gets more interesting. Row reduced echelon form becomes more pivotal, for lack of a better term, when things don't work out the way we think they're going to work out. When we have situations like this. Okay. All right, I'll give you one more. What if I have a matrix like this? So I did all this elementary row operations, and I get this row reduced echelon form of a matrix. I only have one leading one. Do you see that? I only have one pivot. So what are the pivot variables?
Is it just x in this case?
It's just x, because I only have one. And then what are the free variables?
Y and z.
Y and z. And then what would be the dependencies? What are the dependencies between x and y and z? And what are the dependencies? So we'd say what? X is from the first row, right? What's the first row say? The first row says x minus 5y plus z equals 4. So what does x equal? X equals 5y minus z plus 4. So x depends not only on y, but also on z at the same time. And then what is y going to be? Y could be anything, and z could be anything. So then what do we say here? This also has what? The system also represents a system that has what? Infinitely many solutions. And what are my solutions going to look like? What are they going to look like? Well, the first entry is going to be what? 5y minus z plus 4. What's the second entry going to be? Y. What's z going to be? It's just z. Do you see that? Y could be anything. Z could be anything. But the moment you specify what y and z is, x is determined. Hence why it's called the pivot variable, and hence why y and z are free variables. And how are we able to notice that? We're only able to notice that because it's in row reduced echelon form. So row reduced echelon form tells me a lot more about the matrix, especially when you have infinitely many solutions. When you have one solution, we know what to expect. We're gonna get ones across the diagonal. We're gonna get zeros everywhere else. and we get numbers here. So that's what we want. It doesn't always happen though. So we're dealing with things that in a more general sense. Does this make sense?
Yes.
I hope so. I hope so. So we talked about several pieces of terminology, right? We've distinguished between row echelon form, row reduced echelon form. Yeah, row echelon form and row reduced echelon form, REF and RREF. We talked about leading ones, which are the essentially what are called the pivots, back substitution. We talked about the pivot variables and the free variables, and we're able to determine what these are when it's in row reduced echelon form. And so we've done quite a number of things about matrices and associated with elimination, the Gauss-Jordan elimination method. Okay. Any questions up until this point? We're good? Okay. So now that we got used to that, we got accustomed to that. We're going to be talking about different ways to describe systems. And I know we've talked about 2x2 systems, 3x3 linear systems, right? There's another way we categorize systems, and they're called homogeneous systems. Homogeneous system. And we have something that's called non-homogeneous. Of course, we're not dealing with like the more scientific definition for homogeneous. We're not dealing with that definition. We're dealing with the more mathematical term. So what makes a system homogeneous and what makes a system non-homogeneous? It's very simple. A homogeneous system is when the system has something like this. When you have, so I'll give you an example of that. A homogeneous system looks like this. So if I have like 3x plus 4y plus z equals 0, 5x plus 7y plus 3z equals 0, and 5x minus 4y minus 3z equals 0. A homogeneous system is when every equation that you have, right, Mir, every equation that you have has a 0 at the end. That's what a homogeneous system is. So all linear equations when written in standard form equals 0. And guess what non-homogeneous systems are? It's when you write it in standard form for the linear equations, at least one of them is not a 0, meaning that not all of them are 0. So an example for that, I can literally write the same thing. So I'm just going to copy this down. And the moment I see this, like I say this is 0, 0, and I call this a 5. The moment I do that, this is a non-homogeneous system. So this is an indicator. Not all. When written in standard form, not all numbers here RE 0. Okay. Okay. So let me. So for some reason, and you'll see why when we get more acclimated with all this, we like differentiating systems that are homogeneous versus systems that are non-homogeneous. So we'll start with systems that are homogeneous. If you have a system, a homogeneous system, meaning that every equation here that we have has a column of zeros, right? When you augment the matrix, when you augment it, you get zeros, right? So I'll give you another example of this. So if I have something like this, 2x plus y plus 3z equals 0, and I get x plus 2y equals 0, and I get y plus z equals 0. So when I write it in the matrix form, I get 2, 1, 0, 1, 2, 1, 3, 0, 1, and I get all of these to be zeros. Right? So in a homogeneous system, when I write it in its augmented matrix form, I get a column of zeros at the very right of it. And in trying to solve this, can we solve this? How would we solve this?
Could we use the same technique we were using earlier?
Yeah. Which technique is that we're using?
For example, adding row 1. I mean, multiplying 1/2 to row 1.
Right. So we're gonna do 1/2 row 1, right? Negative, right?
Yeah,
And
negative.
we're gonna
And then
add it
add
to
it
row
to
2, and then this becomes row 2, right? So then when I apply this, what's gonna happen? I get 2, 1, 3, right? Then I get 0, 0. This negative half plus 2 is what? 3/2. Negative 3/2. This is what? Negative 3/2. This becomes what? 0, 0, and this becomes, that's it, right? And then I want to get rid of this. What else do I want to do now? Can I make this a 1 now? How do I make this a 1? Multiply this by what? 2/3, and put that, right? And now what does this become? 2, 1, 3, 0, 1, negative 1, 0, 1, 1. And then what do we get? I want to get this. So yes, Chaitanya, you can, it already is homogeneous. You can solve it a number of ways. You can just solve it by substitution if you want, or elimination. But we're trying to use what we've been learning so far, right? Which is putting it in row reduced echelon form. And then the last thing is what I want to get rid of this 0 here, right? So this becomes what? So this becomes negative R2 plus R3. We put it into R3. And then I get 2, 0, 0, 1, 3, 1, negative 1. I do negative 1 plus 1 is 0, negative, negative 1, right? Becomes what? 2. But wait a minute. I want to make the diagonal entries. I want to make them all 1, right? This is already a 1. Check. This is not a 1 yet. This is not a 1 yet. So what do? I can do what? I can do a half of R1, make that R1. I could do half of R2 or R3, make that R3. When I do that, what do I get? I get 1, I get a half, I get 3 halves. I get 0, 1, -1, and I get 0, 0, 1. And then what do I want to do? I want to get rid of this 1 here. What do I have to do? Just add R3 plus R2, put that into R2. Or you could do back substitution. Either way, right? But I just want to write it into row reduced echelon form, and I'll show you why. And this becomes 0, this becomes 1, this becomes 0, this becomes 1, right? This becomes 1 half. This is 3 halves. 0, 0, 0. I'm almost there. I need to get rid of what? I need to get rid of this guy. How do I get rid of that guy? I do what? I do -3 2/3, right? Do you see how it's gonna work out? It's gonna work out. Oh, sorry, I'm gonna add this to R1 and then make that into R1. When I do that, what happens to that 3 halves? This becomes 0, 0, 1. And then what I'm gonna do here, I'm gonna do what? I'm gonna do -2. No, sorry, -1 half. R2 plus R1 goes into R1. When I do that, what happens? This becomes a 0, this becomes a 1, 0, 0. Look what I get. What do I get? I get that x equals 0, y equals 0, z equals 0. That's my solution. The only, do you guys see that? I did all of this to solve this system. So homogeneous sets of equations stay homogeneous despite the form? Of course, no. It's just, this is an example where the homogeneous system, when you solved it, the only solution was 0, 0, 0. And so this is a different kind of way of looking at systems. We're looking at a homogeneous set now. So whenever we have a homogeneous system, and when we solve it, we get 0, 0, 0 as our solution. This is called a trivial solution. This is called the trivial solution. The trivial solution is when you have all zeros for x, y, and z. So the trivial solution is the solution where all variables equal 0 for a homogeneous system. Why is it called trivial? And this word trivial is always used a lot in mathematics. People who do mathematics talk about this is trivial, that's trivial. Is that when you have a system where every equation equals 0, the one that always works is if all the variables are zeros. So in a way, this trivial solution is a solution that always works for homogeneous systems. But not every homogeneous system has only the trivial solution. So let me say that again. The trivial solution works for every homogeneous system. It's trivial because it always will work. It's like the usual suspect. If every variable is a 0 for a homogeneous system, meaning that every equation, right, is equal to 0, then obviously just add a whole bunch of zeros, make all them zeros. They're all going to add up to 0. It's like obvious. But what I'm saying is this is a trivial solution which works for every homogeneous system, but not every homogeneous system has the trivial solution being the only solution. You may have a system that's homogeneous that has more than one solution. And those are called non-trivial. And so we're going to be caring about that a lot more. We're going to be caring about whether systems that are homogeneous have a trivial or more than the trivial solution. But the trivial solution always works for homogeneous systems. Only. Okay? So always works for homogeneous systems. So these terms will creep up. They start to creep up little by little. Okay. I'll give you an example. I'll give you an example of a system that's homogeneous, but that doesn't always have the trivial solution being the only solution. So an example of that. So if I have this 3x plus y plus z plus w equals 0. And then I got 5x minus y plus z minus w equals 0. Do you see, if I make x, y, z, w, if I make all those variables equal to 0, then it solves the system. The trivial solution works. But is that the only one? What happens when we try to solve the system? Let's put it in a row reduced echelon form. This is 3, 1, 1, 1, 5, -1, 1, -1. So let me say something. If I try to write it in its augmented matrix, right? This is the augmented matrix form. What do you notice if I apply the row reduce, if I apply the elimination method to a homogeneous system? That last column here will always be zeros. Like whatever I do to this guy, right? If I multiply it by 5 R1, and I add it to R2 or whatever, this will always be zeros plus zeros. Like these zeros will always be zeros. So in a way, for homogeneous systems only, you don't even need that last column. So that's only for homogeneous systems. So I don't even need it. I don't need it. Do not need. So let me just write this. Hold on. Do not need to augment matrix for homogeneous systems. You don't need it. Can non-trivial solutions exist? Of course. This is an example where non-trivial solutions exist. It's exactly the one. Why is that? Why is this the one? Let's try to write this in row reduced echelon form. How do I write this in row reduced echelon form? This is x, right? This is y, this is z, this is w, right? It has more variables than equations. That's an excellent point. And we'll see that. The number of equations and number of variables have to match, first of all. If they don't, if you have a system like this, where you have 2 equations and 4 unknowns, then there's no other way of it not being non-trivial. Because you're going to have free variables. The moment you have free variables, you have non-trivial solutions for homogeneous systems. But let's write this in row reduced echelon form. What would be the row reduced echelon form of this? So how would I do that? Well, I can do this, right? 1/3 R1, make that R1. What does that look like? 1/3. Sorry, this becomes 1. This is a third. This is a third. This is a third. And I don't remember, we don't need the zeros anymore for the augmented matrix in a homogeneous system. We don't need it anymore because it's just zeros. A column of zeros just becomes a column of zeros again. It's not needed. So I have this. And then I can do what? I can also do 1/5 R3 goes to R3. I mean R2, sorry, pardon me. R2. So this becomes 1 negative a fifth, 1/5 negative a fifth. So there's a lot of fractions here. And then what happens? I can do negative R1 plus R2 goes into R2. So this equation up here, I get 1, 1/3, 1/3, 1/3. This becomes 0. Then I get what? Negative a third minus a fifth, which becomes what? Negative 8/15. So this is negative 8/15. Then I get negative 1/3 plus 1/5. So this becomes 2/8, 15. So 8/15. This is 2/15. And then I get this again, negative 8/15. Does everybody see that? And then I want to do what? So what do I have? I got my pivot variable here. I got my leading one. The only other one that I have that's possible is this one. I can't get any more. I can't get any more because I only have 2 rows in the matrix. So then what do I have? What do I do? I try to make this into a 1, right? How do I make this into a 1? I do what? Negative 15/8 multiplied by R2, make that into R2, right? And so what happens when I do that? I get 1, 1/3, 1/3, 1/3. This becomes 0. This becomes a 1. And this becomes what? Negative a fourth. And this becomes 1. I almost have it in row reduced echelon form. What else do I need to do? I got a 1 here. I got a 1 here. So row reduced echelon form means I need to have zeros below the 1 and zeros above the 1. So I got to get rid of this 1/3. How do I get rid of that 1/3? I do 1/3, negative a third, R2, and add it to R1, put that into R1. So I know it's a lot of fractions here. This is 1, this is 0, this is 0, this is 1. I did it. Row reduced echelon form. I just have to figure out what's next. So I do a third, negative a third. If I do, this is gonna stay. The second row will stay negative a fourth and 1. I just have to worry about what happens up here. So I multiply 1 by negative a third. That's negative third plus a third is what? 0. This becomes 0. And now what does this become? Negative third times negative a fourth is positive 12. And I'm adding that to what? A third. So this is what? 4/4. So I get 5/12. So then what happens? This is row reduced echelon form, RREF. This is X, Y, Z, W. So what are my pivot variables? My pivot variables are X and Y. What are my free variables? My free variables are Z and W. What does that first equation say? X is equal to what? Negative 5/12 Z. And what is Y equal to? 1/4 Z minus W. Do you guys see that? This is non-trivial solutions. So not only do we know that it's infinitely many solutions, now we're having more, I guess, sophistication to it. We're saying it has non-trivial solutions. So we already know that the trivial solution will always work for homogeneous systems. This is an example where we have what are called non-trivial solutions. Does that make sense? So a homogeneous system has either unique trivial solutions or infinitely many. Oh. So a homogeneous system either has a unique solution, and that unique solution has to be the trivial solution, or it has infinitely many solutions, which includes the trivial solution. And can it have no solution? Yeah, you're right. So homogeneous system either has a unique solution, which is just a trivial solution, or has infinitely many, which also includes the trivial solution. That's right. And so there's a theorem related to this called they call it the free variable theorem. For homogeneous systems. And what does it state? It states that if a homogeneous linear system has n unknowns, and the row reduced echelon form has r non-zero rows, aka if you have r non-zero rows, that also means aka you have r leading ones, or aka you have r pivots. So if you have a homogeneous system and you have n unknowns and r of them are pivots, so r of those n are pivots, then what? Then there are, fill in the blank. How many free variables are there? Shouldn't be too hard. No, there's r pivots. So if there's, so basically it's saying like if you have 10 unknowns and 6 of them are pivots, then how many free variables are there? 10 minus 6, which is 4. So the answer should be n minus 4, right? So you subtract. So this is very important. There's a connection, and we'll see more why there's a connection. There's a connection between the number of pivots, obviously, and the number of free variables. The number of pivots plus the number of free variables gives you the number of total unknowns. So the number of pivots, so in other words, let's just write this in other words. The number of pivots plus the number of free variables in a system equals the total number of so I'm gonna call this R. This is n minus R, and this is the total number of unknowns. That's what this theorem is saying. And we kind of get that, right? If you have 2 pivots in a 3x3 system, then there's 1 unknown. There's 1 free variable. If you have, like we had the 2 equations, right? We had 4 variables. We had 2 pivots, then we had 2 free variables. So there's a direct relationship between the number of pivots and the number of free variables. Okay, so we talked a lot about systems and systems. Okay. Okay, I feel like we've done a lot about row elementary row operations, row reduced echelon form, and we did a little bit of homogeneous systems. So we're getting our feet wet. Now I just want to end the next 15 minutes with more computational stuff, more concrete stuff, and those are matrix operations. And this is going to be less, you know, like theoretical and stuff. So these are the matrix operations that you should know when you deal with matrices. So we're going to be moving away from systems, like having equations, and we're going to just be moving towards just having matrices and just dealing with matrices and more matrices. Okay, so there's different ways, right, to represent matrices. We like using capital letters for matrices. So usually we use capital letters for matrices. So usually capital letters are used. To name matrices. And depending upon how many rows, how many columns, right? We have entries. And so how do we denote the entries? We use indices for them. And if we have an uppercase letter, then we use lowercase letters for the entries. So the first row, so this is row 1, right? And this is column 1. So row 1, column 1, we have A11. That's the first row, column 1 entry. And then we have a first row, second column, right? And then we have first row, third column, so on and so forth until we get the first row to the, let's just suppose that there's M columns. So column M, this is A1M. So using these indices will become very, very common in linear algebra. We're going to be using indices a lot. So we have a double index, I guess you can say. The first number here denotes the row. The second number here denotes the column. So then the next row would be what? Row 2 would be what? This is A21. This would be A sub 2, A23, so on and so forth, right? A2M. Does everybody follow this? This is how it's going to basically move along now. And then you go all the way to the nth row, right? Row n. This would be what? AN1, right? Do you see the, this would be AN2. This would be AN3, ... all the way to ANM. So this has how many rows? This is an N by M matrix. So this number here denotes the number of rows, the first number, and this denotes the number of columns. So in a 5 by 3 matrix, you have 5 rows, 3 columns. In a 7 by 8, 10 matrix, you have 7 rows, 10 columns, so on and so forth. So that's how we associate the entries inside our matrix. Okay, and so sometimes we like using N and M to denote the size, right? And we like using random. We like using the indices I, J to indicate the ith row, right? This is the entry. This is the entry of ith row or in of matrix A in the ith row and jth column. So we'll be using this a lot too. It's in the ith row, jth column. So that's a general perspective, right? Okay. So how do we add and subtract matrices? That's pretty simple. How do we add and subtract? Does anybody know how you add or subtract matrices? No? Yeah, so Sam, that's a good point. So you start to see, wait, can we add any kinds of matrices together? We can't. We can only add matrices or subtract matrices that have the same shape. Because there's a natural way to add and subtract matrices, which is what's called component wise. So you add or subtract matrices component wise. What that means is that the prerequisite, so the prereq for this is that matrices must be the same size. They must be. If you don't have matrices with the same size, there's no point of adding them or subtracting them, because then you wouldn't be able to correspond every entry with another entry. There would be some missing. So, like example, if I have 1, 2, 3, 4, right? And I'm adding this to 5, 7, 2, 5, 0. How am I going to add this? Well, it's nice because this is a 2 by 2 matrix plus a 2 by 2 matrix. They're the same size. And then it becomes the first entry in the first row, first column is being added to the first row, first column of the second matrix. So this becomes what? 1 plus 5. This becomes 2 plus 7. This becomes 3 plus 2. And this becomes 4 plus 0. This is almost what's expected, right? You would expect something like this. It seems to flow. Makes sense. So this is 6. This is 9. This is 5. This is 4. So my new matrix is also 2 by 2. Right? And the same thing goes when you subtract. When you subtract, it's the same thing. You subtract 1 minus 5. So if I did the same thing here, 1, 2, 3, 4, 5, 7, 2, 0, right? Subtraction. This is 1 minus 5, 2 minus 7, 3 minus 2, 4 minus 0. So when you subtract everything component wise, you get -4, -5, 1, 0, 4. So adding and subtracting matrices isn't that, I would say, awe-inspiring. So basically, when you have, I think they have a certain, there's a way we can generalize this. So when you add A plus, so if you add A plus B, and you're talking about the ijth term, in the sum A plus B, it's just taking the ith, it's just taking the ith and jth entry of A, and you're adding it to the ith and jth entry of B, which just means the first row, first column of one plus the first row and first column of the other. You can put a minus sign as well. So this is like the general idea of adding and subtracting matrices. It's just that the prerequisite for adding or subtracting matrices is that they have the same size. If you don't have the same size, you can't do this. So it's natural. So that's one operation, right? That's one operation. The second kind of operation that occurs is scalar, is being multiplied by a scalar. Scalar multiplication. So scalar is an important word. A scalar is just a constant. You can think of it. It's another way of saying constant. So what's an example of that? What if I have 2 and I want to multiply it by 1, 2, 3, -4? So what is this? This is a matrix being multiplied by what? A scalar or a constant. So what do you think we're going to do here?
Multiplied all the indices by 2.
Right. How did you know that?
I'm just looking at it like since it's in front of it, I guess you would just multiply it each number as like we did before with the adding. I'd assume that we would just multiply with that number.
Yeah, you can think of multiplication of a scalar as adding this number, this matrix to itself, right? You're basically saying two of these, when you do 2 times something, right? You're basically saying that thing added twice. So when you add it twice, you're just multiplying each entry by 2. So that's exactly right. So you're multiplying 2 times 1, 2 times 3, 2 times 2, 2 times -4. And I get 2, 4, 6, -8. And that would be multiplication. So multiplication is of scalar, of constants. It's also kind of intuitive, right? So if you multiply C times A, right? And you want to know what the ijth term is, you're basically just taking every term and multiply it by every entry of the matrix, just multiplying by that constant. Okay. Now, is that straightforward? So if you have a scalar and you're multiplying it to a matrix, you're multiplying every entry by that scalar. If you're adding and subtracting matrices, making sure you just have to make sure that they have the same size and add each entry component wise by component. So first row, first column, added to the first row, first column of the other matrix, and so on and so forth. The interesting thing is it's not the scalar multiplication and it's not adding and subtracting matrices. It's when you multiply matrices. So matrix multiplication, that is maybe something that some of you haven't seen yet, but I would say this is not an intuitive, oh yeah, that's how you multiply matrices. It's not so intuitive. At least I don't think it is. So like, for example, I'll give you a small example. If I got like 2, 3, 4, 5, and I multiply this by 1, 2, 0, -1. How do you think we're going to multiply these two matrices? Like what would be your guess?
I guess like foiled sort of thing. Like
Yeah, what do you mean by foil?
I don't know, maybe like 2 with 1 and 2 with 0 and then move on. And
2 with 1?
like, yeah, 2 multiplied by 1.
Uh-huh.
2 multiplied by 0.
2 multiplied by 0, and then?
Yeah, and sort of just going through the
Meal.
matrix.
Hold on 1 second. 1 second, guys. Sorry about that. So you said 2 times 1, and then 2 times 0, and then 2 times 2, like that?
Yeah, so I don't know. That would be my guess.
Yeah. Does anybody have any other? That's a interesting take. But the thing is, how do you where would you put these numbers then? Like 2 times 1,
like
and then 2 times 0, and then 2 times 2. Then where do those numbers go?
Yeah, never mind.
I mean, I know. I just want to see who has seen it or who has an intuition to this.
I don't have an intuition, but I think I've seen it before. It's 2 times 1 would be the first entry, then 3 times 2 would be the second entry in the first row. And then the second row would be 4 times 0 as the first entry, and then 5 times -1 as the second entry.
Close.
It would, there is a sum in there that I'm not sure about.
Yeah. So
I know. 2 times 1 plus 2 times 3 would be the first entry, then 2 times 2 plus 3 times 2 as the second entry.
Yes. So this is when things get kind of strange, a little bit. So to get the first entry here, the row 1 and column 1, what you do is you take the row 1 of the first matrix and multiply it by column 1 of the second matrix. And you do it in a very particular way. You take the first entry here, multiply it to the other entry, and you get 2. You get the other entry 3 and multiply it with the other entry 2 here, and you add them. So this is 2 times 1 plus 3 times 2. And that, in a way, I don't know if you've heard of it, but it's called a dot product in a way. You take 2, multiply with this first entry. You take this second entry, multiply it with this second entry, and you add them. You want to get row 1, column 2. What do? You take row 1 of the first matrix, multiply it to column 2 of the second matrix, and do the same thing. Yeah, you do the dot product for each entry. If you guys know what dot product is, you can treat them as vectors. We'll talk about that too. The vector is going to come up. Vectors are going to pop up out of nowhere. So you're going to treat this as a vector. Treat this as a vector. For those of you who don't know what vectors are, it's okay. This is a number. This is a number. This is a number. These numbers. That's what we're going to be dealing with. Take the first entry, multiply them. So this will be 2 times 0 plus 3 times -1. Do the same thing now for row 2, column 1. Row 2 is this row. Column 1 is this column for the second equation, second matrix. 4 times 1 plus 5 times 2. And then you do 4, 5, and then 0, -1. This becomes what? 4 times 0 plus 5 times -1. And so what do you get when you apply this dot product to these columns and rows? You get 2 plus 6, which is 8. 4 plus 10, which is 14. 2 times 0 plus is -3. And you get -5. And this is the product of these two matrices. And we'll talk more about this next time. I will stop the recording right here.